Hello and welcome back to Educator.com and welcome back to physical chemistry. So in the last lesson we started our discussion of molecular spectroscopy. In this lesson we're just going to go ahead and continue with that discussion. Let's get started. Okay, so this is the vibration rotation spectrum for HCl. So here we have the R branch, and the R branch, this is, sometimes you're going to see it like this, and sometimes you're going to see it the other way where the peaks are actually pointing up. It doesn't really matter. The thing you want to remember though is the R branch is the one with the frequencies are increasing. The P branch is the one where the frequencies are decreasing. So in this case, so R isn't left-right. In this case, its frequency is increasing this way. So the R branch is over here. And this is a decreasing frequency, so the P branch is over here. This is not a necessary bit of information. So some of the things that we want to notice here. So let me see if I'm going to go, you know what, I think I'll stick with black. So some things to notice. The first thing you want to notice is that the distance between the lines in the two branches are not equal. In other words, the distance from here to here is not the same as the distance from here to here. You know, we would expect 2b, 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 2b in the P branch, in the R branch, but that's not the case. These are narrower, and as we actually increase, go further along the R branch, the gap tends to get smaller. And as we go further along the P branch, the gap actually gets bigger. So we'll say the distance between lines in the two branches are not equal. The distances are not equal. Now, for the R branch, the gaps get smaller as J increases this way. And for the P branch, the gaps get larger. The gaps get wider. The gaps get wider as J increases. Okay, now we had the following for the harmonic oscillator rigid rotator approximation. We had that the energy Rj, R is the vibrational quantum number, J is the rotational quantum number, so the total energy is equal to the vibrational term plus the rotational term, and we had prime R plus 1/2 plus this constant times J plus 1. And again, R, it goes from 0, 1, 2, and J equals 0, 1, 2, and so on. Now in this particular case, B, the rotational constant, is equal to Planck's constant over 8 pi squared C times the rotational inertia. And the rotational inertia happens to be the reduced mass times the equilibrium bond length squared. Okay. So this is the expression for the energy under the harmonic oscillator rigid rotator approximation. Now, let's take a look at